few videos ago, we looked at the binary phase diagrams of systems with full solubility. In this video, we'll look at the systems with a limited solubility. Again, we'll look at the Gibbs free energy diagrams at different temperatures. The x-axis shows the composition of B, and the y-axis is the Gibbs free energy. We start from a very high temperature, say T1. This curve down here shows the Gibbs free energy of the liquid phase. Note that initially, as you add more and more B into the system, you're adding more entropy, so that lowers the overall Gibbs free energy of the system. After adding 50% of B, the more B you put into the system, the less A you have. In this case, you reduce the entropy, so the Gibbs free energy increases again. The curve on the top shows the Gibbs free energy as a function of B content in the system. Note that it does not have the parabola-like shape like the liquid phase Gibbs free energy curve does. Somewhere in the middle, you see a little bump here that tells us there's an energy penalty here. This energy penalty is caused by the limited solubility between A and B. If we look at which phase will be present at this temperature, since the liquid phase has a lower Gibbs free energy at all compositions, then the material or the system will remain liquid. Next, let's decrease the temperature. In this system, we assume A has a higher melting temperature, so as you decrease the temperature, the A rich phase will come out as a solid phase first. Let's have a closer look at this Gibbs free energy diagram. Notice we can draw a straight line that is a tangent for both the solid and the liquid Gibbs free energy curves. From the previous video, we know this is a sign of phase separation. In fact, between the region enclosed by these two tangent points, the chemical potential of all the elements remains the same, so you can have two different phases coexist. Let's look at what are the possible phases present in this compositional space. In the very small region on the left, that is from 100% A to the first tangent point, because the Gibbs free energy of the solid phase is lower than the liquid phase, we know this will be solid. From the second tangent point to 100% B, the Gibbs free energy of the liquid phase is lower than that of solid, so this will be liquid. For the region between the two tangent points, we have phase separation, that both the liquid and the solid phases coexist. Let's reduce the temperature further, and in this case, you can see there are two straight lines that are tangents of the solid and the liquid Gibbs free energy curves. On both ends, since the solid Gibbs free energy curves have lower energy, so they are solids. In the middle, the liquid has a lower Gibbs free energy, so it's liquid, and in between, these are the solid and liquid coexisting regions. Let's decrease the temperature further. We have a single straight line that is tangent to both the solid and the liquid Gibbs free energy curves. Again, on both ends, we have the solid phases, and between the tangent points, we have the liquid and the solid phase coexisting. Let's further reduce the temperature. In this case, we have one straight line that is only tangent to the solid Gibbs free energy curve. Again, on both ends of this compositional space, we have solid phases. Next, I want to challenge you. What is the phase, or what are the phases between these two tangent points? I will give you 5 seconds to think about it. The answer is we will also have the solid phase between these two tangent points. You may wonder why there's no liquid phase at all, especially around 50% A and 50% B. The liquid phase actually has a lower Gibbs free energy than the solid phase. Then why are we only getting the solid phases? The answer lies on where the tangent points are. The tangent points are alpha 1 and alpha 2 in this example. Therefore, in between these two tangent points, the phase separation will be alpha 1 and alpha 2. Both alpha 1 and alpha 2 are solid phases, so there's no liquid present in this condition. In fact, you can apply this understanding to the previous higher temperature cases and check whether this principle is correct. Now, we are ready to compile everything together to form the phase diagram of systems with limited solubility. At a very high temperature, at T1, across the compositional space, everything's liquid. Go to a lower temperature, T2. As B increases, we have solid, liquids plus solid, and liquid. Further lowering the temperature to T3, as B increases, we have solid, liquid plus solid, liquid, liquid plus solid, and liquid. Further decreasing the temperature to T5, we only have the solid phase. Now, you should be familiar with the binary phase diagrams of systems with full solubility versus the limited solubility. On the left, that shows an example of the binary phase diagram of a system with full solubility. The signature is that in the phase separation region, it has a lenticular shape. In contrast, for the systems with limited solubility, the phase diagram has a rabbit shape, or if you are from a younger generation, you can say this is the Pikachu shape. On top, there are two pointy ears, and down the bottom, you can actually draw two eyes here. In this diagram, there is a special point I'd like to draw your attention to. This is called the eutectic point. When the phase transformation goes through the eutectic point, you will not get liquid and solid phases coexisting. All the liquid will turn into solid instantaneously. Another thing I'd like to draw your attention to is that for the systems with limited solubility, not all phase diagrams will adopt the Pikachu form. You can get phase diagrams looking something like the one in the middle, or something complicated like the one on the right. In this video and the past few videos, we focused on the binary phase diagrams. In the next video, we will lightly touch upon the ternary phase diagrams to teach you how to read it and how to use it.